All right, we're ready to continue with the lesson series on creating and using a memory. So far, the story has been getting information into the brain. We talked about the encoding stage and the storage stage. Now it's time to realize the importance of retrieval. We must be able to get the information out of our brain by reactivating those very memory traces formed during the learning event. So let's say we have a brain here. We have just studied once, but we haven't gone to sleep yet. So we're left with weak cortical memory traces, but a strong hippocampal memory trace that has linked together these cortical memory traces, forming a unified sort of memory trace. Now, how do we retrieve, then, the memory for the information we just studied? Scientists think what we need to be able to do is to activate the cortical memory traces in unison. And what they think is going on when we attempt to retrieve a memory is some cue is given, like a question about information we were just studying, and then we use the contents of working memory to search our long-term memory system in the hope that we can reactivate these weak memory traces. But scientists suspect that early on, after just one study session, we're going to need the assistance of that strong hippocampal memory trace. And without this strong hippocampal memory trace, the idea is that we would fail to retrieve these cortical memory traces. Let's see how we could draw that. So here we go. Somebody asked us a question about what we were just studying. It does successfully activate the strong hippocampal memory trace for that study information, and then the activity will be sent up to the cortical memory traces. Remember, there's two-way connection between the cortex and the hippocampus and the cortex. So here the hippocampal memory trace is being used to reactivate, right? So it was physically linked to those cortical memory traces, and so it has the ability to reactivate those cortical memory traces. And if we're successfully reactivating those weak memory traces in unison, they will share their information with the working memory system, and we will have a conscious experience of retrieving the information that was asked of us. Now, why do scientists think that the hippocampus is so important in retrieving newly learned information? Well, the evidence then takes us back to our neurological patients like HM. You'll recall he had epilepsy, and to treat his epilepsy, surgeons removed parts of his brain. Over here on the right, we see the underside of the brain with the temporal cortex here. A lot of that tissue was removed on both sides. Here down bottom here, we see a slice through the brain, and here the location of the hippocampus on each side. And again, the hippocampus was removed on both sides of his brain. So HM could not retrieve recently learned information, so the inference, the conclusion was that the removed tissue somehow played a role in that memory process. So here's the situation for HM. We have a brain that can form weak memory traces of new things that he is attempting to learn, but without a hippocampus, there's no way to link those cortical memory traces. You'll recall in a normal brain, we're going to make a strong hippocampal memory trace that is linking the cortical memory traces. Well, HM is unable to do that because he does not have that critical brain region, the hippocampus. And furthermore, if you don't have a hippocampus, you can't use the hippocampal memory trace, the index, to reactivate those weak cortical memory traces. So HM can't form the hippocampal memory trace because he doesn't have a hippocampus, and he can't use the hippocampal memory trace to reactivate the cortical memory traces because he doesn't have a hippocampus. So we're going to have retrieval failure then for both HM and Clive. You'll recall Clive had a viral infection that destroyed his hippocampus on both sides. So we have failure because the brain is unable to reactivate these weak memory traces without the hippocampus, the intact functioning hippocampus. And so this is the reason why scientists think that you got to have a functioning hippocampus to retrieve recently learned information, because that information is stored in the cortex with weak memory traces, and we need the hippocampus to assist us in reactivating those cortical memory traces. Now, even beyond this, then, a brain like HM or Clive is not going to be able to strengthen these cortical memory traces. You'll recall during sleep we do the consolidation process where we fire up the hippocampal memory traces to strengthen the cortical memory traces. Well, if you don't have a hippocampus, you can't do that important memory processing during sleep. So the brains of HM and Clive, they can go through the world and have experiences and learn things in a sense. Their brain is responding. The cortex is making weak memory traces, but they will be unable then to retrieve that information. And over time, they will be unable to strengthen those cortical memory traces, so they will appear to us as being incapable of learning anything new. Now, interestingly, HM could retrieve remote memories. These would be memories for things that happen prior to the surgery, years before the surgery, like events of his childhood, for example. So why would that be? Well, let's take a look at the brain on the left here. Here we have HM as a child or a young adult. HM had a functioning hippocampus, so all the stuff he was attempting to learn, he was successful in making strong hippocampal memory traces that could be used to retrieve the weak memory traces in the cortex. But not only that, because he had an intact hippocampus, then when he would go to sleep after a day's learning, he would do the consolidation process. So he'd be able to strengthen these cortical memory traces for all that stuff he was learning early in his life. So along comes the surgery in the 1950s. He has lots of information strongly stored in the cortex, and so when they removed his hippocampus, his frontal cortex retrieval systems were still successful in activating those strong memory traces and achieving retrieval success. So the reason why HM and Clive could access remote memories is because those memories were already well consolidated in the cortex, and you don't need a hippocampus to retrieve those kinds of well-stored memory traces. So the study of these neurological patients led scientists to some important conclusions. HM's memory performance suggested that remote memories were stored in the cortex, not the hippocampus, but in the cortex, but that a functioning hippocampus was necessary to create those long-term cortical memories. We now know that sleep is precisely the time in which the temporary memories in the hippocampus are reactivated and used to strengthen the appropriate cortical memory traces. So here's the hippocampus here in this brain, and we'll just say here's some cortex over here. And it's this communication between the hippocampus and the cortex that's going to build those long-term cortical memories, those strong cortical memories. But we have to have a functioning hippocampus so that then when we go to sleep, we can do that consolidation and strengthen those cortical memory traces. If you don't have a hippocampus, first of all, you can't link together all those cortical memory traces that are forming as you go about and attempt to learn things. And then neither can you do consolidation during sleep, so you'll always be left with weak memory traces in the cortex that cannot be retrieved successfully from the frontal cortex retrieval systems. So at this point then, if we go back to our sort of flowchart diagram, this process of sort of converting short-term memories in the working memory system into the long-term system requires a functioning hippocampus so that we can consolidate a memory in the cortex. We can strengthen those cortical memory traces. Using our computer analogy, HM and Clive suffer from a failure to write strong data to the hard drive. Again, the hard drive would represent our long-term memory system in the cerebral cortex, and the working memory would be like the short-term memory system, the RAM in a computer. Well, the problem with HM and Clive is that whatever's in their working memory cannot be, in a sense, written to the hard drive in a strong way. They will have weak cortical memory traces for stuff they're attempting to learn, but there's no way to strengthen those memory traces in the hard drive without a hippocampus. On the other hand, if they already had strong memory traces stored in the cortex, they can retrieve that information, as we saw with remote memories. So because those remote experiences were well consolidated in the cortex, they can be retrieved at this time even without a hippocampus. But again, there's a failure of this analogy. Remember, on a computer, all the information is stored with equal strength, as it were. But in human brains, it's different. We can have weak memories and strong memories. And so the problem with HM and Clive is they cannot strengthen those weak cortical memory traces, and so they will always be failing to retrieve any of these weak cortical memory traces, and that will appear to us like they can't learn any new information about their world. So we're lifelong learners, or we hope that we will encourage people to be lifelong learners. And the reason we can be lifelong learners is because we've got lots of storage space in our cerebral cortex, and we've got this fascinating structure, the hippocampus, that is always going to be refreshed and ready to learn new stuff, and then help us store strong memories for all the stuff that we want to learn over the course of a life. In the next lesson, we'll look at the value of using retrieval practice spaced out in time as part of our study technique. We will see that this study technique will help us in two ways. It will help us strengthen our cortical memory traces, as well as strengthen the retrieval pathways that are responsible for locating our memories so that we can successfully retrieve them.